Hey team, you ready for our second video in our chemical compounds journey together? Chemistry coach coming at you. Let's look specifically at ionic compounds. We've talked about bits and pieces of this, but let's formalize it all in one nice spot. Hopefully this is review for you. Pretty straightforward mathematics. Although a majority of you can probably just do all of this in your head, which is great. But if not, I'll show you structural ways of doing it. No big deal. So remember, we were talking about chemical formulas, and for ionic compounds, you have positively charged cations, negatively charged anions, put together in a ratio such as that the overall compound must be neutral. Right? So we got to know, is that cation a +2, +3, +5? Is the anion a -1, -3, -4, whatever it is? Put them in the proper ratio to get a neutral compound. That's our overlying thinking process. That is the formula unit, right? It shows that ratio of cations to anions. So three to four things really I want you to get from this particular video, right? Be able to look at a periodic table and predict the charge of any nonmetal, and then some of the metals. We're going to call them type 1 metals, whereas type 2 metals we won't be able to predict from the periodic table because they'll have multiple options. But there's a small subset of metals that only form one type of cation, either always a +1 or a +2, always a +3. So I'll point those out on the periodic table so that you can just look at the periodic table and go, whoop, hey, aluminum's a +3, sodium's a +1, boom, 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 boom. Oh, vanadium, don't know. That could be many different options. So we want to know those type 1 versus type 2 metals. Once we know that, you should be able to take those ion charges, the charge of the cation, the charge of the anion, and be able to write the formula unit by getting a net neutral compound. Many of you know how to do that already. Well, vice versa, if I give you a formula unit, you should be able to extract from that what is the cation and its charge, and what is the anion and its charge, right? Most of you can probably just do that in your head. If not, I'll show you an algebraic way to do that. And last but not least, know your polyatomic ions, right? Most of what we do is monatomic ions, a single atom with a charge. But what if you've got multiple atoms, a molecule with a charge like PO43- or NO3- or NH4+? No way to predict the charges at this point in the class. So I'm sorry, I'm not really big on forcing you to memorize stuff, but in my class, metric conversions, polyatomic ions, and type 1 metals. Just make note cards and just crush those in your head. It will really save you pain in the long run, knowing your polyatomic ions. So I have a list that I'll show you when we get to that. So let's start with the first one, predicting charges of simple elements from the periodic table. So get out your periodic table. All right, gang, let's do the first part of this. Predict. Now, we can't write formula units if we don't know the charges of the cations and anions, right? So we need to be able to grab our trusty-dusty periodic table of doom and find, right? And remember, you got the staircase line. You've got the nonmetals here, metalloids along it, metals to the left. So let's focus on nonmetals now, because nonmetals and metals tend to be opposites in a lot of situations. So for nonmetals, all we're really looking to do is, and we'll look at it in terms of electrons in a much later chapter, but for now, I'll just show you some simple shortcuts. Really, you look at the nearest the noble gases here. We're going to find out that those are more stable forms. So really, when an element or an atom combines with something else or reacts with something else, its driving force is to be like the noble gas electronically. So all these elements want to be isoelectronic, iso means same number of electrons as the nearest noble gas. Now for nonmetals, which are on the right, the nearest noble gas is the next one, right? So for, fluorine, the nearest noble gas is neon. So it wants to be like Mike, it wants to be like neon. So all you got to do is just count the number of columns away, and that will be the numerical value of the anion, or the negative charge. So fluorine, for example, is 1 away, so it'd be -1. Oxygen would be -2. Nitrogen would be 1, 2, -3. Carbon would be 1, 2, 3, 4, -4, if it was an anion. So very easy to do. So we looked at fluoride. So very simply, that would be a -1. So you can write it as F minus. So you can either say -1 or F, and you put the charge to the upper right quadrant, and you don't include the 1 in there. So let's look at sulfur. Sulfur is right there, so that's 1, 2 away from argon. So sulfur forms a -2. Pretty simple to do, right? Phosphorus, right? Phosphorus is right there, so that's 1, 2, 3 away from argon. So phosphorus would pick up 3 electrons to become a -3 charged anion. And tellurium, even these metalloids that are along the staircase line, if they act like a nonmetal, you'd follow this. So if tellurium was acting like selenium, sulfur, and oxygen, it'd be 2 away from xenon and form a -2 charge. Now we're going to be naming compounds later on down the road, but if we did name these, you just take the root name of the element, so fluor from fluorine, and just add the suffix -ide. So that's fluoride. Let's do that in this color. So this would be the fluoride. The fluoride, not flour, fluoride ion. Phosphorus, you'd think it'd be phosphoride, but it's one of those exceptions like sulfur as well. So it's the phosphide ion. And some people don't put the ion, they just say phosphide. But if it's an ion by itself, I like to put ion on the end of the name. Sulfur, right? Instead of sulfuride, we go sulfide. So that's the sulfide ion. And tellurium, take the root tellure. It's not in Colorado or something. I think I went to Telluride, Colorado once. Telluride. Telluride ion. Not a big deal, right? Metals are a little trickier because we're going to have to break metals into 2 categories. Type 1 metals only form 1 type of charge, which we can predict from the periodic table. Type 2 metals form multiple charges, so we can't predict which one it is from the periodic table. We would need extra information. So let's talk about the type 1 metals. For type 1 metals, and I'll identify which ones they are, you're going to want to have these memorized. There's not too many options, so it should be pretty straightforward. So memorize the type 1 metals, but not the type 2, because if it's not a type 1, it must be a type 2. So these are metals that only form 1 type of cation charge. So only a +1, or only a +3, or only a +2. Doesn't have multiple options like a +2 or a +3. That'd be a type 2 metal, right? And just like with noble gases, the driving force for these elements reacting is to be isoelectronic, have the same number of electrons as the closest noble gas. Now, for metals, since they're on the right-hand side, they're going to be closer to the prior one. Nonmetals are closer to the next one. So you're just looking for the closest prior noble gas and count the number of columns away. There's also another trick we can use for these type 1 metals. It's equal to the group number. So you can use either way to do that. So we'll do both ways. So let's do a couple examples. I'm going to list through all the type 1 metals for you and write those down on a note card or something, carry it around in your pocket, tattoo it on your arm, whatever you got to do. All right, write this down. Your type 1 metals, group 1A, all right? So outside of hydrogen, of course. So all of these, your alkali metals, that's your group 1A. They're always going to form a +1 charge, group 1, +1, and they're 1 away, right? So boom. So to get from lithium with 3 electrons to helium with 2, it has to lose 1. Sodium has to lose 1 to become this. Potassium has to lose 1 to become argon, right? So they just lose 1 electron, boop, 1 column to the left, you're good to go. But group 1, +1. Also the group 2A metals, the alkaline earth metals, that's your group 2A, form a +2 charge because they go lose 2 electrons to become isoelectronic with the prior noble gas. Hey, that's why we love that group 1A, group 2A, right? So those are your main type 1 metals. There's some exceptions to them. So let's go ahead and write the answers up here. So sodium, for example, if I had sodium chloride, you'd look at the periodic table. That's group 1A, an alkaline metal. So sodium is a +1 charge. You don't do the +1. You don't do the 1, just the plus. Rubidium would be rubidium with a +1 charge. Now, when we name these, now with metals, with anions, you took the root of the element and added the IDE suffix. So chloride ion, fluoride ion, bromide ion. We don't do that with metals, which causes some confusion. You just retain the original name. So this would be the sodium ion, and this would be the rubidium ion. Rubidium ion. If you don't say ion, that creates a lot of issues, because if you just say sodium and you don't clarify, is that the neutral element sodium or is that the +1 cation sodium? That's the difference between life and death, because if you're taking Na plus from salt, you're fine. If you eat a chunk of neutral elemental sodium, you're dead. Fire-breathing dragon, dead, not good, okay? So very important to specify for metals, whether you're talking about the neutral metal or the cation form of the metal. Hugely important. So for group 2A, these form a +2 charge equal to the group number. Always. There's no exceptions to that in nature. Of course, you get a big enough laser, blah, 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 I can make it a +3 or +5, but naturally it would form a +2. So barium would form a +2 charge, right? It's in that second column. Strontium would form a +2 charge, right? Any of these alkaline earth metals, +2, +2, +2, +2, +2, +2 for everybody. Get rid of 2 electrons. And that would be the barium ion and the strontium ion. If you named them, you don't change the original name of the element. You just add the word ion on the end. So know your group 1A and your group 2A. Those are type 1 metals. Always form 1 charge. You just look at your periodic table, whip your head around. First column +1, second column +2. There are a few exceptions. Some of these babies, some of these transition metals in the middle, because of unique electron structures we'll learn later, only form 1 possible type of cation charge. So if we look through, we find aluminum, which is in group 3, 3A. Not the boron, but aluminum. Now, all of these have a tendency to form a +3. The aluminum, gallium, indium, thallium. What the heck is that? Nihonium. But aluminum is a special one. It's 3 away. If you go back 3, 1, 2, 3 to get to neon, it forms a +3 charge. So aluminum is always going to be Al +3. Or you could just say +3 charge. It's either aluminum 3+ or just +3. Silver. No way we could predict at this point, but it turns out silver only forms a +1 charge. That's something you're just going to have to memorize. So silver is +1 or Ag+. Zinc and cadmium. So here's zinc, right on the end of the transition metals there, and cadmium. They only form a +2 charge naturally. So this would be a +2 or a zinc 2+ and cadmium 2+. We'll find out why later. Some people will put nickel in there as well. I do not. I use nickel as either a +1 or +2, but depending who's teaching your class, go with that. So group 1A, group 2A, aluminum, silver, cadmium, zinc. Memorize those, memorize their charges, and life will be easier for you later. So let's look up type 2 metals, and then we'll get into writing some formula units. Type 2 metals get a little tricky. And again, how do you know it's a type 2 metal? It's not a type 1 metal. Woo! So if it's not in group 1A, it's not an alkaline metal, it's not an alkaline earth metal in group 2A, aluminum, silver, cadmium, or zinc, it must be a type 2 metal. Don't even bother. You cannot look at the periodic table and say, hey, manganese is a +2. How do you know? Because manganese, I've seen manganese as a +5, a +3, a +2. You don't know. There's no way you can tell which specific one of the multiple charges it can form from the periodic table. You need more information. Right? You either have to have it provided to you. Oh, here's iron with a +3 charge. Here's lead with a +2 charge or a +4. It has to be specified. Or you're given the actual formula unit, and from the formula unit, knowing the anion charge, we can determine algebraically, like reverse engineering, we could figure out the positive charge of that type 2 metal. So type 1 metals you can determine from the periodic table. Type 2 metals you cannot know a specific charge. You can know it may be this or this, but you need more information to figure out the specific one. So there you go. We can start putting some formula units together. Let's do it. This should be pretty easy. I'm assuming you already know how to do this, but let's look at it again. If we want to write a formula unit, of course, you need to be able to predict the charges if they're not provided for you. But again, just find the cation-anion ratio that gives you the lowest integer. You need the lowest integer ratio between cations and anions to give you a neutral compound. That is your formula unit. So the best way to do it, I've seen people talk about the Crisscross Method and all that. I just say find the lowest or least common multiple between those. So if I have manganese 2, that's a type 2 metal, so I had to provide that for you. You couldn't get it from the periodic table. Selenium, you could have predicted from the periodic table, right? Because selenium is right there. So that's 2, boom, boop, 2 away from krypton, so that's a -2. Notice they're equal and opposite, right? So the lowest common multiple is 2. Right, so to get a +2, I need 1 manganese. To get a -2, I need 1 selenium or selenide ion. So that would be a 1-to-1 ratio. Whenever they're equal and opposite, +3 -3, +1 -1, +2 -2, they go together in a 1-to-1 ratio. Fumble! So when I put these together, I need 1 manganese for every 1 sulfur. Oh, that's selenium. I got excited. I glanced over at the sulfur there. So 1-to-1 ratio. And we'll name those later. That'll be a separate thing. Don't worry about naming them now. But pretty easy to do. 1-to-1 ratio. We love that. But what if they're not equal and opposite? Well, then they're obviously not going to go in a 1-to-1 ratio. So I've seen people use the crisscross method. That doesn't work all the time. Crisscross meaning how many of the scandium cations do I need? Well, what's the charge on the sulfur? 2. So I need 2 scandium ions. How many sulfide ions do I need? Well, what's the charge on the scandium? 3. So I need 3 of those. Right, so you crisscross the charges, and that tells you the subscript of the other one. That works for most things, right? So it's better to find the common multiple between 3 and 2, which is 6, right? So I need 2 scandiums to get to a +6. I need 3 sulfurs to get, or sulfides, to get to a -6. So 2 times 3 is +6, 3 times 2 is -6. +6 plus -6 is 0. But you can see how the crisscross work. That becomes this, that becomes that. That works great. That doesn't work for things that, what if you had a +4 and a -2? Right? You couldn't do the crisscross on that because the common multiple is 4, not 8. The lowest common multiple is 4, not 8. So watch out for that. All right? But very simple, very straightforward once you know the charges. Right? Scandium, of course, would be a type 2 metal. I would have to give that to you. Sulfur, you could look as 2 away from its nearest noble gas as a -2. So type 1 metals you can predict. Type 2 metals I have to give to you. So let's look at a situation. What if I give you a formula unit? So I give you this, and then you got to figure out what is the cation and its charge, what's the anion and its charge. A little bit tougher to do, I think. It's easier to go from the charges to the formula unit than the other direction. So let's practice that. All right, here we go. Pretty much, it depends. When you're given a formula unit, so I gave you 2 examples here. I'm giving you the formula unit, and I want to know what's the charge on the cation here, what's the charge on the anion here, what's the charge on that cation, what's the charge of that anion. Depends on the nonmetals, you can just figure out from the periodic table. That's easy, right? But the metal, if it's a type 1 metal, you can figure it out from the periodic table. Type 2 metals, you can't, so you got to get it from this by reverse engineering, and I'll show you how to do that. So this first one should be pretty straightforward for you. Magnesium, look in here and you go, oh, magnesium, that's an alkaline earth metal. That's a type 2A metal. That's a type, right? It's a group, not a type 2A, a group 2A metal. That's always a +2. That's considered the type 1 metal, right? Here's the type 1 metals, aluminum, cadmium, silver, and zinc. Those are always the same charge. So you should be able to look at magnesium and go, boom, boom. That's always a +2. Always, always, always. So here, magnesium is a +2 charge, or you could go magnesium 2+. Either way. Bromide, right? You can figure it out knowing that that's a +2. It must be a -1. But bromine here is a nonmetal. That's 1 away from krypton, so it's a -1. So you'll always know the nonmetals from the periodic table. So bromine, let's do this in blue. Or you could go Br-. Right? No fancy stuff. You can just look them up on the periodic table. You're good to go. But what if we have a type 2 metal? This is a type 2 metal. So you cannot look at the periodic table. What is TB? What is that? Is that terbium? Hardest part's finding the darn thing on the periodic table. It is terbium, way down here. What is that, a lanthanide? That's one of the inner transition metals. There's no way we know what the charge is from the periodic table. We can predict maybe a couple possibilities later, but not a specific one. So we're going to have to reverse engineer it and get it from the oxygen. We do know the oxide, correct? So let's do that. Whoa, I am just slippy fingers today. But oxygen is a -2, or you could go O2 minus. The terbium, we don't know. Right? We have no idea. We can't figure if they're in periodic table. So let's reverse engineer it. Let's do some algebra. If you can just see in your head that it's a +3, then you're good. If not, just do this. Take the total number of cations, so the terbium plus the terbium, plus the oxide plus oxide plus oxide, you add them all together, should equal 0. So 2 times the charge of the terbium plus 3 times the charge of the oxide should equal 0. It has to because it's a neutral compound. So we can do this. Let's take the terbium. We have 2 of them, right? Everybody agree you have 2 terbiums? We don't know the charge, so let's call it X. So let's say 2 times X, the unknown cation charge of terbium. And then we've got the oxygen. There's 3 of them, correct? So you take the number of those cations times its charge, plus the number of the anions times its charge, which is a -2, should equal 0. That's the charge of the compound. Now just solve for X, right? So let's move this to the other side. So 2X will be, that's a -6 moves over a +6. So X must be, divide 2 by both sides, so X is a +3. Right? So we know that the terbium is a +3. If you can just see that in your head, great. But if you're stuck, just do the algebra here. Take the number of cations times its charge, in this case X, plus the number of anions times its charge here, in case, and you always know this one, equals 0 because it's a neutral compound. Boom, solve for X. Not a big deal, guys. Let's look at some polyatomic ions. All right, we've got the bane to all young chemists' existence, polyatomic ions. Are you ready for this? Here we go. So polyatomic ions, we've been only looking at monatomic ions at this point, right? So Na+, Br-, those kinds of things. These are essentially charged molecules. Poly meaning many atoms with a charge. That's really all that means. So you'll see, like I said, an NO3-, a PO3, PO4 3-, something like that. So you see, usually, not always, usually 2 or more elements with subscripts. Sometimes it's just 1 element with a subscript. So it doesn't matter what the elements are, just that you have 2 or more atoms. Okay, they could be all from the same element or not. That's not imperative. But most of the time you'll see 2 or more elements with a charge, with a certain number of subscripts. You need to memorize these. There's just no way around it. You want to do it as fast as you can, however you do it. Whether it's on your phone and you're just looking at that while you're, bored at a party or something. Whatever works for you. I used to do it during breakfast all the time, walking across campus. Boring date at dinner. Hey, this chemistry is more exciting than you. Blah, 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 and memorize it. Here, test me on these. When you're writing formula units, right, you only are worried about the charge ratios. It doesn't matter if it's NO3- or Cl- or F- or OH-. It doesn't matter. They all have a -1 charge. Right? It's irrelevant. The identity doesn't matter. Just the charge matters to find the lowest common multiple. So don't freak out if you got some weird C2H3O2-. It's just a -1 charge. Don't worry about how nasty it looks. If you have more, if you have more than 1 polyatomic ion, in order to draw the correct formula unit and get the proper charge ratio to give a neutral compound, you've got to put that polyatomic ion in parentheses. So put a parentheses around that polyatomic ion and then put the subscript. Otherwise, it looks really weird. So we'll do a couple examples that show you that. So the polyatomic ions, I'm not going to go through all the details. Just print out my list here. Different teachers have different lists. This is my list of some of the most common ones. Just know these, all right? No way to predict the charges at this point. There's some nice tricks from the periodic table you may have seen before to know that, but just brute force works great. Commonly, you're going to see an element, usually a nonmetal, combined with oxygen most of the time, not always. But here you see two combinations, right? You see NO2 minus and NO3 minus. Commonly when you see that, you'll take the root of the non-oxygen and add the suffix ITE for the one with fewer oxygens and ATE with the one with more oxygens. So NO2 minus is nitrate ion, NO3 minus, nitrite, and NO3 minus is nitrate. So ITE suffix is fewer oxygens, ATE suffix is more oxygen. So whenever you see an 8 or an ite, you know it's a polyatomic ion, not a monatomic ion. Those have the IDE for metals, right? Nonmetals. So same thing with sulfur. You have sulfite, SO3 minus, and sulfate ion, SO4 minuses. The only time you'll see more than that is these halogens form these oxoanion series or oxyanion series. So you get the ClO minus, ClO2 minus, ClO3, ClO4. You're like, whoa, you get 4 combinations. The bromines can do that. The iodines can do that. And they're all a -1 charge. So we take the middle two and call that the 8 and the ite. So the ClO3 minus is the chlorate, the ClO2 minus is the chlorite. The ClO minus is 1 less oxygen than ClO2. So it's 1 less than chlorite. So we use a prefix, hypo means less than. So hypochlorite is 1 less oxygen than chlorite. If you have 1 oxygen more than chlorate, we use the prefix per. Per means more. So ClO4 minus is 1 more per oxygen than chlorate, so per chlorate ion. You could have per bromate, per iodate, per fluorate. So you actually have 16 combinations with that crazy mess. Sometimes you'll see a metal with the oxygen, like permanganate. A couple chromiums, chromate, dichromate. We'll see acetate, the only really main organic one you're going to use, acetate ion, C2H3O2 minus. OH minus, this is one of the rare ones that ends in an IDE suffix. That gets a little confusing because mostly that's reserved for, you know, oxide or something. It's a monatomic non-metal ion. So hydroxide is a common one that you'll see all the time, represents base, right? Peroxide, you've heard of that. That's the O. So that's one where you have only one element, O2 with a 2 minus charge. So it's 2 O minuses bound together, right? It's kind of a weird one, peroxide. There's another weird one with an "ide" ending, cyanide. I'm sure you've all heard of cyanide, CN minus. Here's some of the few, almost all of these are negative anions. So very few positive polyatomic cations. The ammonium ion, NH4 plus, by far the most common, comes from NH3, ammonia, gaining an H plus. And then the mercury 1 or mercurous ion is 2 Hg pluses bound together to form Hg2 plus. That's a weird one. This is a small list. There are way more polyatomic ions than this, but these are the only ones that are fair game on my exams that I would expect you to know. If I give you one that's not on there, I will provide you its charge and name. Fair game, we good? Memorize this. Let's do a couple compounds with them and we're done. All right, my recommendation, pause the video. Give me the formula units for these bad daddies right here. Hopefully they're not going to be too bad. Don't worry about what it looks like. Just look at the charts. That's a +1. That's a -3. What's the lowest common multiple between 1 and 3? 3! So I need 1 of the phosphides and 3 of the ammoniums. So let's take ammonium. Now let me show you how this doesn't work out. We need 3 of them, right? Let's say we don't put the parentheses on there. What? That doesn't make any sense. It's not 1 nitrogen with 43 hydrogens, right? So you need to put the ammonium ion in parentheses with a sub 3. You see that? So if you only have 1, you don't need the parentheses. But if you have 2 or more of those polyatomic ions, you gotta put it in parentheses. Otherwise, it looks really, really weird. Tin's a +4, carbonate's a -2. Lowest common multiple is 4, not 8. So to get 4, we need 1 tin. To get 4, we need 2 carbonates. Whoops, that's an ugly looking parentheses. See that? That's one where the crisscross doesn't work. So it's a nice little trick to crisscross, but it doesn't work all the time. So, you know, it's no different than what we did before. Just use parentheses if you got more than 1 polyatomic ion. You're good to go, my friends. Work on this. Make note cards or fold this up in your pocket and carry it around with you and wear it down. Don't let it go through the laundry. You guys rock.